Hello, fellow science enthusiasts. Welcome back to Investigating the Universe. Today, we're embarking on a thought-provoking journey, one that takes us deep into the core of one of the most intriguing debates in the annals of physics. Einstein's quantum riddle, encapsulated by the renowned EPR paradox. As we set the stage, let's rewind to the early 20th century, a time of scientific revolution when the world was just beginning to grapple with the bizarre and bewildering principles of quantum mechanics. This groundbreaking theory was promising to redefine our understanding of the universe, offering a new lens to view the behavior of its tiniest constituents. In the midst of this scientific upheaval emerged a figure of unparalleled intellect and profound curiosity, Albert Einstein. Known for his monumental contributions to the world of science, Einstein was not one to blindly accept a theory, however revolutionary it might be. He was a skeptic, a questioner, a challenger, and the nascent field of quantum mechanics was no exception. Einstein found himself at odds with the core tenets of quantum mechanics, particularly its inherent uncertainty and probabilistic nature. He questioned, he probed, he challenged. His skepticism was not aimed at undermining the theory, but at refining it, extracting the absolute truth from its enigmatic depths. This audacious spirit of inquiry led him to propose what has come to be known as the EPR Paradox, a thought experiment that seemed to expose the flaws in the very foundations of quantum mechanics. This was not merely a scientific disagreement, it was a clash of philosophies, a battle of ideologies. On one side was Einstein, a staunch believer in deterministic laws governing the universe. On the other side were the quantum physicists, who embraced the probabilistic nature of the quantum world and the strange phenomena it entailed. This was the beginning of a debate that would shake the world of physics to its core, a debate that continues to this day, challenging our understanding of the universe and the laws that govern it. Enter Albert Einstein, a scientific giant challenging the very essence of this groundbreaking theory. First, let's grasp the basics. Quantum mechanics, a seemingly bizarre theory that dares to challenge our conventional understanding of the universe. Here, the laws of classical physics that we've come to know and love take a backseat, making way for a realm that's truly mind-boggling. Now, what makes quantum mechanics so fascinating? To start, it's all about the tiniest particles in the universe, the building blocks of matter. These include electrons, protons, neutrons, and even smaller particles like quarks. In this realm, these particles don't behave like the everyday objects we're used to. One of the key principles of quantum mechanics is the concept of superposition. This means that a particle can exist in multiple states at once. Yes, you heard that right. For instance, an electron in a quantum state might be in several places simultaneously. It's only when we measure it that the electron chooses a position to collapse into. This leads us to another foundational aspect of quantum mechanics, its inherent uncertainty. Known as the Heisenberg uncertainty principle, it states that you can't simultaneously know both the exact position and momentum of a particle. The more precisely one measures one quantity, the less precisely the other can be known. This isn't due to any limitations in our measurement tools, but a fundamental aspect of nature itself. Finally, quantum mechanics is probabilistic, not deterministic. This means we can't predict with absolute certainty the outcomes of measurements. Instead, we can only calculate the probabilities of different results. In this strange quantum world, particles behave more like waves of probability than solid objects. They exist in multiple states at once, and it's only the act of measurement that forces them into a single state. It's a probabilistic world, and our ability to predict outcomes is limited to probabilities rather than certainties. Now, let's delve into the heart of the matter, the EPR paradox. In the quantum world, particles can be in multiple states all at once, a phenomenon known as superposition. But this wasn't quite enough for Einstein, Podolsky, and Rosen. They wanted certainty in a world where uncertainty was the rule, not the exception. So they proposed a thought experiment, a kind of quantum puzzler, if you will. They imagined two particles in an entangled state, separated by a vast distance. The spooky part, measure one particle and you instantly know the state of the other, no matter how far apart they are. This seemed to defy the limit of the speed of light for information transfer, a cornerstone of Einstein's theory of relativity. Einstein called it spooky action at a distance, and it didn't sit well with him. He, along with Podolsky and Rosen, argued that quantum mechanics as it stood was incomplete, that there must be some hidden variables, some underlying layer of reality that we weren't seeing, that would explain this instant communication and bring back determinism into the picture. But what were these elusive hidden variables? They were thought to be parameters that would determine the properties of particles in advance. In essence, if we could discover these hidden variables, we could predict with certainty the outcome of quantum measurements. This was a bold proposition, one that challenged the fundamental principles of quantum mechanics. It was as if Einstein, Podolsky, and Rosen were daring the quantum world, saying, "There's more to you than meets the eye." The EPR paradox ignited a firestorm in the scientific community. It questioned the very fabric of quantum mechanics and left physicists grappling with the question, could there be a deeper deterministic theory that governs the quantum world, or is the universe inherently probabilistic? They questioned the completeness of the theory, suggesting that there might be hidden variables determining particle properties yet to be discovered. In response, Niels Bohr defended the probabilistic nature of quantum mechanics. Bohr, a key figure in the early development of quantum theory, stood firm against Einstein's hidden variables proposition. He argued that quantum mechanics was not incomplete as Einstein suggested, but rather it was a complete theory in its own right. He maintained that the theory's inherent uncertainty was not due to missing variables, but a fundamental aspect of nature itself. Bohr introduced a concept that was as baffling as it was revolutionary: quantum entanglement. This is the idea that particles can become so deeply linked that the state of one instantaneously affects the state of the other, no matter the distance between them. This extraordinary phenomenon seemed to contradict our everyday understanding of the world. Yet it was a cornerstone of Bohr's argument. He embraced the concept of entanglement, where particles become interconnected in ways that defy classical intuition. As time progressed, experiments were conducted to test the predictions of quantum mechanics and the implications of entanglement. The scientific world wasn't simply content to let the EPR paradox remain a thought experiment. Instead, they turned to the laboratory where theory meets reality. One of the most significant developments came in the form of Bell's theorem. Proposed by physicist John Bell in the 1960s, this theorem provided a way to test whether or not there were hidden variables at play, just as Einstein, Podolsky, and Rosen had suggested. Fast forward to more recent times, and advancements continue to be made in the realm of quantum entanglement studies. From demonstrating entanglement between larger and more complex systems to teleporting information using entangled particles, the boundaries of our understanding continue to be pushed. These developments serve as a testament to the enduring intrigue of the EPR paradox. Scientists have sought to unravel the mysteries at the heart of Einstein's quantum riddle. Fast forward to today, and the echoes of Einstein's quantum riddle still reverberate through the halls of physics. The EPR paradox, once a theoretical debate, now forms the cornerstone of our understanding of the quantum world. This paradox has challenged us to question the nature of reality, sparking a revolution in our thought process. As we delve deeper into the realms of quantum mechanics, the influence of the EPR paradox becomes more evident. It's not just about entangled particles or hidden variables anymore, it's about the very fabric of our universe. The EPR paradox has also fueled advancements in quantum computing, quantum cryptography, and quantum teleportation, to name a few. These are not just theoretical concepts but real-world applications that are reshaping our technological landscape. The debate that started with Einstein, Podolsky, and Rosen is far from over. The debate has profoundly influenced our understanding of the quantum world and continues to inspire new avenues of research and exploration. As we wrap up our journey into the depths of Einstein's quantum riddle, we've scratched the surface of a debate that transcends time. We've explored the birth of quantum mechanics, its bold departure from classical physics, and the audacious challenge presented by Einstein, Podolsky, and Rosen. They questioned the completeness of this revolutionary theory, suggesting the existence of hidden variables yet to be discovered. We've delved into Bohr's counterargument, embracing the strange world of entanglement where particles become interconnected in ways that defy our classical intuition. We've traced the developments since the EPR debate, from Bell's theorem to the latest research in quantum entanglement, and seen how these scientific endeavors have sought to unravel the mysteries at the heart of Einstein's quantum riddle. This debate has profoundly shaped our understanding of the quantum world, continuously inspiring new research and exploration. The EPR paradox remains a pivotal moment in the history of physics, challenging our preconceptions and pushing the boundaries of our understanding. Thank you for joining us on this exploration of Einstein's quantum riddle. If you enjoyed this video, don't forget to like, subscribe, and share your thoughts in the comments below. Until next time, keep exploring the wonders of the universe. This is Investigating the Universe, signing off.